We have learned two connections between magnetism and electric fields or electricity. First, every charge in motion produces its own magnetic field. Second, if you send a charge through an external magnetic field, something else's magnetic field, then the charge will feel a magnetic force. We can calculate that magnetic force F in two different scenarios. The first equation is for a single moving charge, and the second scenario is for lots of charges, or in other words, a current in a wire. In the top equation, Q is the charge, V is the speed of the charge. B, of course, is the magnetic field strength, or the flux density. In the bottom equation, I is the current traveling, and L is the length of the wire. So these equations allow us to calculate the magnitude. That's why we use these equations. The magnitude of the magnetic force. But which way does that magnetic force point? You might think, well, with the field lines, right? Like if you have some electric field like this, and you put a charge, then that charge gets pushed in a direction with the field lines. Likewise, if you take the planet Earth, and you zoom in to a single person holding a ball, here they are, there is a gravitational field pulling down. So where would the ball get pulled? Where is the direction of the force on the ball? Down with the gravitational field. So far, every scenario we've learned says the force is parallel to the field lines. That will not be the case for magnetic forces. For a magnetic force, it will always have a direction perpendicular to the magnetic field lines. And that's kind of weird. Look at this picture down here. Before we consider this rule that you see, just look at the picture. The field points like this from north to south. So you've got two magnets. And yet, the magnetic force is not in the direction of the field. Instead, you can see right here clearly, the magnetic force is perpendicular to the field lines. And that is a very weird idea. But it gets weirder. Not only is the magnetic force perpendicular to the field lines, which point like this, it's also perpendicular to the velocity. So we need a rule to work out these directions, which say the magnetic force is perpendicular to the field lines, and the magnetic force is perpendicular to the velocity. How do we work this out? Already it sounds pretty weird. We use something called the right-hand rule, but it's different from this right-hand rule. So let's just call this one the first right-hand rule. And what we see now, this is the second right-hand rule. So what is this right-hand rule? The right-hand rule says, stick out your hand. Again, your thumb points with the direction of the charges where they're moving, so thumb points with the velocity. Your fingers look like field lines, so they point with the magnetic field. And wherever your palm faces, so the palm here is facing to the right, that's the direction of the magnetic force. So how do you remember this? Well, when you hold out your palm, that's how you slap. You slap somebody with your palm, right? So the palm shows us where the force, it faces where the force points. The thumb looks like a wire, so it shows where the current or the velocity is directed, and your fingers look like field lines, so they show us the magnetic field. This right-hand rule is what we use for positive charges, or if they just say for current. If you are dealing with negative charges, simply use your left hand. If they say an electron is moving. Let's take a look at some examples which are on page 17 of our notes to work this out. Okay, we have to imagine our hand. We have this negative charge, and it feels a force to the left, to the right. Because the charge is negative, I use my left hand, and it says, okay, the magnetic field points into the page as indicated by these X's. We have to find the direction of the charge's velocity. Okay, so let's use the right-hand rule, except we're using our left hand, right? Because it's a negative charge. So this is a box just for three-dimensional orientation. Just so we can orient, here's the box, and I'm going to try to draw a hand showing us how to model this scenario. Okay, so our fingers point with the magnetic field lines. So our fingers have to point into the page, like this. Our thumb is what we're trying to figure out, because the thumb shows us the velocity. So that's the question. Where does our thumb point? All right, what else do we know? Well, our palm has to face with the force. Okay, so my palm would be pointing to the right. And when you hold out your hand like this, where is your thumb sticking? It sticks up. So the velocity of the charge is upward. Let's try number 3. A negative charge, so use your left hand, is passing through a uniform magnetic field that points down the page. So there are field lines pointing down. Okay? The charge is traveling to the right. We have to find the direction of the magnetic force. The magnetic force is indicated by our palm. So let's draw the picture, and you can use your hand and stick your hand in this orientation. Your thumb, you're using your left hand now, your thumb has to point to the left with the velocity. Your fingers have to point down with the magnetic field. And where does your palm face? If you imagine a 3D picture, your palm is facing out of the page. So the force is out of the page. Thanks for watching.